Good afternoon. I'm Dave West. I am the third person in Object Guild that they mentioned earlier. I started Smalltalk programming with methods in 1988 and wrote a simulation of a Buddhist monastery for my anthropology advisor. It was really a cool little project. In the 90s, I started teaching at the university in Minneapolis in the United States. And between 1990 and 1996, everybody, well, 95% of the people in Minneapolis that became professional Smalltalk programmers or object-oriented programmers came through my university program or my consulting practice. So the entire city of Minneapolis, the entire professional body in Minneapolis doing Smalltalk was my fault. But then, unfortunately, between 96 and 2000, I watched as three very specific business decisions, not technical, not language, not anything. Three business decisions destroyed Smalltalk and ascended Java. And nobody was interested in objects anymore. So that was kind of a painful period. But I watched from afar as Smalltalk kept alive and thriving in ESUG, and you cannot imagine how many years I wished that I had the opportunity to come here, and now I am finally here, and I'm really happy. So, okay, one final thing. This is a precisely timed presentation. So I warn you, if you ask questions, I'm going to answer them. So we're going to talk about natural systems design. And what you all know and what you have been hearing about all week and probably most of your professional lives is all about the artificial, building, engineering, designing things that are artificial systems. The computer is an artificial system. And that's what you have been learning how to do for a long time. Software engineering, 1968. The most unfortunate metaphor in our profession ever. Software engineering. The idea that we can build things like software the same way that we build buildings and bridges. Artificial things. At the time, it didn't seem like it was that bad of an idea. It seemed like it was kind of a natural that software engineering is just applied computer science. Computer science is all about how you compute things and do things and how you write programming and all of these kinds of things. So it seemed like a good idea. Turned out to be a very unfortunate metaphor. Herbert Simon wrote the book, Sciences of the Artificial, which was the de facto Bible of software engineering. You cannot find a software engineering principle anywhere that is not discussed by Mr. Simon, Dr. Simon, Nobel Prize winner, Dr. Simon. So engineering is what we have been doing for 70 years. Engineering can do some really remarkable things. Engineering can build some really incredible bridges. This is in China, the Yangon Bridge in China. Engineering is more than capable of building something like Paulo Soleri's arcologies. That is a building that houses 500,000 people, all of the manufacturing, all of the retail, all of the infrastructure, all of the energy generation, everything else for 500,000 people in a single building. We could build that. There's absolutely no reason in the world that we could not build that. Engineering is a remarkable, remarkable thing. Unfortunately, engineering can't do some things. Can't build a city. Can't engineer a city. There's not an engineered city on the planet. There's a lot of design cities on the planet that were sterile, lifeless, inert, until people came in and messed everything up and made them a livable place to live. couldn't engineer it. You couldn't engineer the web. You can engineer the internet, can't engineer the web. Not possible. You can't engineer life. Yes, we have recombinant DNA. Yes, we have CRISPR. Yes, we have all of these other kinds of things that lets us muck around. But we can twist things. We can probably destroy things very effectively. We certainly can't build them. Which brings us to the problem that is confronting all of us and will confront us more and more and more as we move into the future. In the mid-90s, the United States in the 2005, 2006 era, the U.S. Department of Defense commissioned a study by Carnegie Mellon, or it was housed at Carnegie Mellon. They got the grant. Carnegie Mellon is home of the Software Engineering Institute and is kind of the premier center for software engineering. But DoD said, hey, we're confronting all of these global problems, global intelligence. How do we keep track of everything that's going on in the whole world? How do we do intelligence where we have to listen to gazillions of phone calls every day and figure out what you're talking about? And don't know. So let's study it. So they commissioned the study. They performed the study. That particular study was just on ultra large scale systems, global systems. But it very quickly merged into the notion of complex systems and complex adaptive systems, hence the metaphor ultra large scale complex adaptive systems. These are natural systems. These are things that occur in the real world. These are things that nature builds that we can't engineer, the cities, the life, things of this sort. They're complex. Complex means that there are aspects of them that you literally cannot know. So unlike an engineering problem where you can, in principle, know everything, you can know all the variables, you can know all the relationships, and design as a matter of optimization, when it comes to these natural systems, there are things that you literally cannot know until they pop up in your face and say, gotcha. Then you say, what? How did I not know that? Natural systems are living systems. They are highly dynamic. They change constantly. They evolve constantly. They are not static. So even if you understood the system perfectly today, next week, you're not going to have a clue. Well, a little clue, but not much. They are self-adapting, self-organizing, so they don't like being managed or controlled any more than your 2-year-old child. They're living systems. But they create real problems, particularly for people that are trying to develop software or trying to build or trying to intervene in these kinds of systems. So how do we deal with these kinds of things? Well, we start off with a different perspective. So Alan Kay, kind of the object godfather, once said that the right perspective is worth 80 IQ points. Engineering is not the right perspective. So you've got to find a new one. And we're going to have to start figuring out exactly what that new perspective is going to be. There's a lot of work being done in complex systems. There's a lot of work done in biology, in horticulture, in cultural anthropology. All of these things are very rich fields for where we're going to find the right metaphor and the right perspective to proceed with things in the future. Fortunately, we have a tool that, again, it came out of biology. A guy named von Bertalanffy, who was a biology. He was the founder of general systems theory. And general systems theory would say, what can we understand from a biological system that will help us understand an engineering system, which will help us understand a highway system, city systems, things of this sort. So they were cross-systems disciplinary in their orientation. And because of that, they had to have a very simple kind of a model of how you model a system. And they came up with the simplest thing possible. A system is nothing more than a set of elements and the relationships among them. You can define any system with that definition. Guarantee it. Any system. What will differentiate a normal system, an engineerable system, from a complex living adaptive system is the pace of change, how often the relationships change, how often the relationships are totally situational. This relationship exists from time T1 to time 2, disappears, comes back at time 17, disappears again, or these objects do, these elements do. But you can model this is a very simple model, and you can model anything that way. It's a model that you should be familiar with because it's the same model that was proposed, metaphorically at least, in the very early days of objects. A system is a set of objects and the relationships among them, and everything is an object, including the relationships. And so if you build your objects in this fashion, and if you use behavior the way that systems living systems do, as the criteria for differentiating between your elements or your objects, then you are guaranteed to have a very powerful model for building and designing what it is that you want to build in the area of complex systems. There are some real specific challenges that are posed by UCLS with software in particular in mind, if you're trying to build a software system. One is they abhor centralized control. Nature abhors a dictator as much as it abhors a vacuum. Won't stand for it. You cannot find centralized control anywhere in nature. It's all collaborative. It's all self-organizing. It's all peer-to-peer. No centralized control. The internet is pretty good at not having centralized control either, which is one of the reasons that the internet can fail locally without ever having any big impact on the internet as a whole. That's another one of the challenges, by the way. Autonomy. A biological cell is autonomous. Yes, it gets together and gangs up with other cells to do interesting kinds of things, but no cell controls another. They are all autonomous. Objects should be autonomous too. And then we do these nasty little things to objects, like make them friends of each other so that they have access to each other's internals. No, 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 no. That's a total violation of autonomy. How would you like it if I stuck wires in your head, which I could, and make you dance around, by pressing buttons up here on my console? You wouldn't like that. Your objects don't either. Even if they're code, they still don't like it. Integrating human beings into your system, into your software system. We are so accustomed to treating human beings as if they are mere users, mere clients, and mostly idiots. They cannot understand this elegant interface that I just built. They sit there and stare at it and wonder. I wonder about the future of the human race with people that are that dumb. But that's the way that we have been thinking about them. And that's the way we've been thinking about you. You're not a human being. You're a mere commodity. If you can fit the profile of the job description, you're our man or our woman or our whatever. You're a commodity. You're not a person. And in fact, software engineering itself is built on the premise that you're an idiot too. And the only way that we can trust you to build software is if we give you a very meticulous, very ritualistic method and mandate that you follow it. That's what the CMM was all about, by the way. So, but now you're going to have to change your attitude. You're going to have to recognize that human beings have capabilities. They have innate abilities. They have innate gifts that cannot be replicated in a computer or in a piece of software. All of this hype about AI is so far from the mark of what it means to be a human intelligent entity that it's nearly ridiculous. You're going to have to quit figuring out how to eliminate humans and figure out how to integrate them into your system. as little black computational boxes with their own interfaces. That's a big challenge. Adaptation and continuous evolution. Nothing is static in a living system. You do not have time for a project that takes 6 months to 3 years to complete. It's irrelevant and a waste of money by the time it's delivered. You've got to be able to come in and keep pace with this continuous change, continuous adaptation, continuous evolution. And then the local failure that I mentioned earlier. If you ever write a piece of software that has the capability of crashing that piece of software in toto, you've got it wrong. And not only do you have it wrong, you also need to go the little extra mile of keeping your failures local. And that means the resolution of those failures local, and the resolution of those failures done by the objects in situ, not by running back to the programming shop to have someone fix it. So a lot of things about machine learning and a lot of things that are about artificial intelligence that are really going to be applicable in the future world of software are going to be around this area of self-repairing. A little bit about the evolution as well. There is some promising directions that things can go. And Smalltalk and objects are at the foundation of these promising opportunities. There are some things that you can actually start doing today as you think about how you design your programs and how you design your objects. The first and the most important one is the one that was totally overlooked. When objects were proposed as an idea and as a metaphor, an object was a homunculus. It was an intelligent entity that did things, that made contributions to the world. It took about 60 seconds, and oh no, an object is an abstract data type. Oh no, an object is a data entity, a data structure that has animation, that has some functions attached to it. And that's the kind of objects that most people have been writing ever since. But if you can go back to the original ideas, go back to the works of people like Kent Beck, Rebecca Wurfsbrock, or even me, and look at the idea of objects as behavioral entities, it makes a order of magnitude difference in the elegance, the simplicity, and the power of the systems that you build with those objects. Everything an object. So I mentioned in the system model that relationships are objects too. Well, everything should be an object. You can go back in the early 90s when there were publications abounding like Object Magazine, like the Journal of Object-Oriented Programming, and you can find tons of articles on how to reify things that are not objects into making them first-class objects. A message, a protocol, the memory structure that an object might have, or its description. There's all kinds of ways of doing these things. You can even reify a method as an object and make it dynamic, borrow some ideas from self to do that kind of thing. You can explore their ways of reifying the Smalltalk code itself so that it's an object, and you can change the code by sending messages to the blocks of code. It's all doable. It's all been done. It's not done very much. The user illusion. One of the most interesting developments in software, in the practice of software development over the last few years, has been the focus on domain-driven design, or other kinds of things that force you to look at the real world and how things work in the real world, instead of looking inside of the computer and imagining from a whole cloth what things might do or how they might work inside of the machine. The domain won't steal you wrong. There are still some things that are not optimal, in looking at that, but the world is your model. And what you do in software should preserve, and this is key to bringing people into the system, is that you've got to maintain their user illusion. They've got to feel like the person that they're working with inside of the computer is identical to the person they're working with on the chair on the other side of the desk. And if you can't maintain that illusion, you're going to lose people. But it's doable. It's been done. Program is a script. So instead of writing code, sit down and write a theatrical script for a play or a movie. And think about how you give your objects the cues that they need, what kinds of lines they have to deliver to each other in order to bring the movie or advance the plot and bring it to an optimal conclusion. Figure out what kind of props you have to give them. But think about it from the metaphor of writing a movie script or a theater script instead of writing a program which is addressed to the computer. Runtime modification is a big deal. And again, it's doable. It's been done. You can send messages to objects that are out there deployed and operating in the real world and have them change their behavior. You can have them change the information that they're aware of. You can do all kinds of things simply by sending a message while they are working. It's not hard, but it's not done very much, but it's possible. Now the real challenges, the things that you're going to have to go home and put your thinking hats on and figure out how you're going to do this. First of all, you need a ubiquitous Smalltalk operating system. One that takes your platform, again, as a collection of hardware services to begin with, but also a collection of local objects that can provide services. And your operating system operates primarily as a dating service. An object can come to the platform, ask the operating system, do you have anybody or anything on site that can help me with this problem? And the operating system can say, yes, here they are. From that point, the thing itself manages itself. So I don't have to have an operating system with interrupts and everything else to figure out how to get different flows of data stored on my disk drive. The disk drive will set up its queue, handle things in its own fashion, in its own manner, one after the other. It's a very different way of thinking about things. Again, it's probably doable, but it is something that's a challenge that's going to require some significant thought. Smalltalk on bare hardware. This has been done, but it's been mostly abandoned. I used to actually own, back in 91, 92, something like that, a wristwatch with a little itty bitty tiny keyboard that you had to use a stylus that had Smalltalk running on it, the full development environment running on that wristwatch. No operating system, nothing between Smalltalk and the bare hardware. When Dan Ingalls and Alan Kay went to Disney after they left Apple, they again built a device. It was a little device that they were going to use in the park that had Smalltalk running on bare hardware on that device. And it not only managed your waiting time, you could sign up to go on the Ferris wheel or the lightsaber show or whatever, but it would also amuse you while you were standing in line. It would also notify you of the restaurants and all the other things they could sell you, of course. But it was Smalltalk running on bare hardware. You need that in order to build that ubiquitous object operating system. Free-range objects. So Alan Kay used to say that every object should have its own URL. He didn't say it a lot because at that time you didn't have the URL namespace available for every object to have one. Now you have an object or you could have a URL for every grain of sand on the planet. So there are enough out there. And it does a lot of things besides just give add to the objects autonomy and give them a unique identity, which is their URL at creation. It also allows them to move freely from your platform, your ubiquitous OS operating system platform, find what they need, and then also move to where they're being used. So objects can freely move around the internet to where they are being used. The image. This was the biggest complaint about the rest of the world about Smalltalk from day one. That damn image. How do I get out of there? How do I get, nice little tight little executables the way that I do with all my other programming languages? The image is a really cool thing. It is an essential thing for doing development, things of this sort, but it's not exactly the ideal delivery platform. You can't have free-ranging objects that are still somehow or other bound and contained within an image. They've got to escape it. And so what you should start thinking to do, perhaps, and this is one of the objectives that I'm working on to describe exactly how to do this with natural systems design, is how you use reality as your image, as your deployment image at least, and keep your existing Smalltalk image as your development image. Needs to be done. And then the really kicker, everything has to be an object. Everything has to be Smalltalk. And you've got to lose the full stack. If you're doing Pharo and this and that and this framework and this other framework and this other framework, it's never going to work. You've got to figure out how to make everything one fundamental, ubiquitous, universal language in order to make this work. And this is going to be a real challenge because you're not paid to do that. You're paid to learn the full stack and to do things that keep the management happy. So like biological systems, the ULS is a software-based ULS. It's software-based because it's not all software. Those humans are in there too, and other things. Is a dynamic community of interdependent and competing organisms. People, computing devices, organizations in a complex world. This quote is from that ULS study where they were trying to define exactly the research objectives that people would have to achieve in order to reach this kind of goal. So that's it. Any questions?
What do you envision the objects to live from? I eat food.
So what do objects live from, i.e. food? Well, human objects are going to go to the buffet down the street, just like they do right now. Software objects are probably going to require one of two different kinds of things: energy and information. And energy and information are, in fact, interchangeable. Just brush up on your quantum physics, and you will find out that the entire universe is information, and so you can have objects that are basically consumers of this information/energy and get along quite nicely. This is horribly theoretic, not a practical answer at all, but that is the direction that the answer is probably going to come from. Yes?
Why would you say that everything has to be Smalltalk?
Why does everything have to be Smalltalk? Because you've got a head start. You've been doing so many things right for so long, and a whole bunch of things that you've forgotten about, that you have a head start. That's the only reason. It doesn't have to be Smalltalk. It probably won't be literally Smalltalk. It will probably be something a lot more like, this is a 1989 book that I have on my shelf, Object-Oriented Assembler. That's probably the future.